Now we will discuss the magnetic field due to a current flowing through a circular conductor. Now here it is an experimental arrangement consisting of a horizontal drawing sheet. A cardboard sheet is held in the horizontal plane. Two holes are made on the cardboard sheet and a long wire is bent in the form of a circular loop. One end of the wire passes through the hole on the left side and the other end passes through the hole on the right side of the cardboard, and the other two free ends are connected to a battery in series with the plug key. Can you imagine the setup like this? So a long wire is taken, it is bent in the form of a circular loop. One end passes through one hole, the other end passes through the other hole, which are made on a horizontal drawing sheet. Okay, and the two ends of the circular loop are connected to battery as shown. Okay, so one end of the wire is connected to the positive of the battery and the other end is connected to the negative of the battery in series with what? A plug key. Now there is no current flowing through the conductor as per this diagram. Then you sprinkle some iron filings, okay, some iron powder. So iron filings are sprinkled randomly over the drawing sheet. On the cardboard sheet, you sprinkle some iron filings randomly, and now you close the circuit by plugging in the key. Okay, the plug key is now closed, and the current will send that is, the current will be sent by the battery from the positive terminal. That current is called as conventional current. Okay, so the conventional current continuously, if you follow the path, means at this point the current will flow in the upward direction. See, you follow the path from the positive terminal of the battery, the current is continuously flowing and it is continuously entering the circular loop in this direction. It flows in this direction, and here at this end it is in the downward direction, and then it flows downwards and it passes towards the negative of the battery. This is a closed loop. So the current has started from the positive terminal of the battery and it has ended at the negative terminal of the battery. We have to observe only the 2 points very keenly. So at this point the current is in the upward direction, and at this point the current is in the downward direction. Now applying right hand thumb rule at these two end points. Okay, now you will see that at this end point the current is in the upward direction. So the magnetic field pattern should be what? In the anti-clockwise direction. In the anti-clockwise direction, is it not? Like that in the other end, what? The current is in which direction? Downward direction. You see here the current is in the downward direction. So now you see that the remaining figures are in the clockwise direction. So at these two end points there will be magnetic field surrounding the conductor, and at the left end it will be in the anti-clockwise direction, and in the right end the magnetic field will be in the clockwise direction. Okay, and in between the two ends the magnetic field how it will be? It was tested, okay, by sprinkling some iron filings. These iron filings were attracted towards the conductor. How? Because there is a magnetic field produced by the current flowing through the conductor. Due to the magnetic field, the iron filings will be attracted and they will be following circular patterns around the conductor. So you see at the left end, the iron filings were forming circular pattern like this. Okay, they were forming circular pattern. Similarly at this end also, the iron filings were attracted along a circular pattern like this. Okay, so this is the pattern of the magnetic field surrounding the conductor at the two ends. Then as the distance increases from the two holes, as the distance increases, the field lines were like this, and at the center of the field lines were like this. You see that you see the direction of the magnetic field. Okay, since at the left end the current is flowing in the upward direction means the magnetic field is turning leftward, that is in the anti-clockwise direction. And at the right end, this point, the current is in the downward direction. It is in the downward direction. As a result, the magnetic field is in the clockwise direction. Okay. Then at the center of the loop, you can see straight lines. Okay. At the center of the loop, the current flowing through the conductor will produce a uniform magnetic field. As per this diagram, the arrow is pointing upwards. Actually the arrow is lying on the horizontal cardboard sheet, because the cardboard sheet is horizontal, is it not? So the magnetic field is along the horizontal direction, that is perpendicular to the circular loop. The circular loop is in the vertical plane, is it not? But the cardboard is what? Horizontal, perpendicular to the board it is, okay? So the magnetic field line is now passing into the board. It is passing into the board. Suppose if you change the direction of the current, suppose if negative and positive terminals are reversed, means what will happen? The current will flow in the reverse direction. As a result, here the current will be upward and here the current will be downward. And here the magnetic field will be in the anti-clockwise direction. Here it will be in the clockwise direction. So that now the middle portion, how the magnetic field will be, it will be pointing towards you like this. It will be pointing from the board, perpendicular to the plane of the board. Understand? So now, in this picture, since the vertical plane contains the circular loop, the magnetic field will be perpendicular to the circular loop only, either inward into the board or outward away from the board pointing towards you. So here also we can apply what? The right hand thumb rule only. Thumb rule is not only true for straight conductors, for circular conductor also thumb rule is true. Understand? So when the current is flowing in the upward direction, means the magnetic field will be in the anti-clockwise direction. When the current is flowing in the downward direction, means what? The magnetic field will be in the clockwise direction. Now what is the symbol for magnetic field? Magnetic field is what? B. It is a vector quantity because it has both magnitude as well as direction. It is a vector quantity. And let I be the current flowing through the conductor. That is the conventional current. Here also, this magnetic field strength, okay, magnetic field strength is directly proportional to the current. When you increase the current, the strength of the magnetic field can be increased. And here only one turn of the circular loop I have considered. Suppose if you take 2 turns, 3 turns, 4 turns, 100 turns, if you increase the number of turns for the same current, the strength of the magnetic field can be increased several times. Okay, though we have considered only one circular loop here, number of loop is equal to 1. But what will happen if you increase the number of loops, then also magnetic field pattern will be the same. At the 2 ends it will be circular, at the center it will be straight and uniform. But the strength of the magnetic field will increase. So it was found that this B, strength of the magnetic field, is proportional to the number of turns N. N is the number of turns of the circular loop. And you take the circle is having a radius, okay? The radius of the circular loop is A. This time A is the radius of the circular loop. It is found that this magnetic field strength is inversely proportional to the radius of the circular loop. So here N means what? Number of turns, okay? I means what? Current flowing through the conductor. And A means what? The radius of the circular loop. Radius of the circular loop. So on how many factors the magnetic field depends? It is 3 factors. It is directly proportional to the current flowing through the conductor. And it is directly proportional to the number of circular loops in the conductor. And it is inversely proportional to the radius of the circular loop. Understand? In addition to that, what must be the 4th factor? Can you guess? It is the medium surrounding the conductor, whether it is kept in vacuum or air, in water or oil or whatever medium where it is placed. So naturally there are 4 factors for this case. So I will write that the magnetic field, the strength of the magnetic field is equal to mu naught Ni divided by 2A. So this is, once again I am repeating, my dear students, this is for the NTSE exam and for the students of HOTS standard. Understand? So these expressions are not given in the textbook directly, but it is better if you remember for appearing in the competitive exams like NTSE and other exams. Understand? So what is the expression for the magnetic field strength for a current carrying circular conductor? B is the strength of the magnetic field. It is also called intensity of the magnetic field, okay, and it is equal to mu naught Ni by 2a, where mu naught is called, okay, once again I am repeating students, this is called as a permeability. Permeability. It is the ability of the medium to permit the magnetic flow through it. So this is the permeability of a free space. Permeability of a free space, okay, and its value also, this is 4 pi into 10 to the power of minus 7 Henry per meter. All these are advanced topics for you. Only this expression you can remember. Otherwise, these informations and all you need not remember, okay. Okay, my dear students, in the earlier example, when the conductor was straight, the magnetic field surrounding the conductor was circular. And in this case, when the conductor is circular, the magnetic field at its center along its axis is straight. So how does the magnetic field pass through this circular loop perpendicular to the plane of the circular loop through its center and along its axis, okay. So this is the diagrammatic representation. I hope you must have understood. The next category is what, instead of a circular conductor, we are going to see a solenoid, okay. Shall I rub the board? Okay. The next topic is magnetic field due to current through a solenoid. So previously we have discussed the magnetic field due to a straight conductor carrying current and a circular loop carrying current. Like that, now what will be the magnetic field due to a solenoid carrying current? First of all, what is meant by a solenoid? Let us find out. See, you can see this cylindrical shaped coil. This is a cylindrical shaped coil which is having circular windings of the wire. You take a cylinder, okay, made up of an insulator, and you take a long copper wire and wind circular turns or loops over the cylinder. Then this spiral shaped coil or cylindrical shaped coil with circular windings only is called as a solenoid. So as usual, the two ends of the solenoid, the two end points of the solenoid are connected to the positive and negative terminals of a battery. So one end of the solenoid is connected to the positive of the battery, the other end is connected to the negative of the battery through a key which is opened now. So when I close this key, means the conventional current will start from which terminal as usual? From the positive. The conventional current will start from the positive terminal. And you will see that in every turn, in every circular turn, the current will be traveling. The current from this side, this end if you see, means the current will be flowing in the clockwise direction, okay. So this is the direction of current through every loop like this. And finally the current is flowing towards the negative terminal. So the solenoid is now called as a current carrying solenoid. As a result, magnetic field will be produced at different points. Now the pattern of the magnetic field will be like this, okay. The pattern of the magnetic field will be like this. So this is acting as the south pole and this is acting as the north pole. So we already know the properties of magnetic lines of force. They always start from the north pole and point towards the south pole. So the magnetic lines are passing towards the south pole here and they are starting going outward from the north pole. And at other points, the pattern of the magnetic field will be like this, okay. The pattern of the magnetic field will be like this. So outside the solenoid, there is no magnetic field. Understand? The magnetic field outside the solenoid will be equal to 0. And where will be the magnetic field due to the solenoid is only inside the solenoid, at all points inside the solenoid. And this field is a uniform magnetic field, and this field lines passes through the axis of the solenoid. See here, if you measure the magnetic field strength at this point, center, or at this end, or at this end, at all points, the magnetic field B will be the same strength. Such a magnetic field having the same strength at all points is called as the uniform magnetic field. And such uniform magnetic field due to solenoid is represented by parallel lines, horizontal lines which are parallel to each other. So this will be the pattern of the magnetic field which is found inside the solenoid along the axis of the solenoid. And outside the solenoid, the magnetic lines of force, they will be cancelling each other, so that the net magnetic field due to the solenoid outside the solenoid is 0, and inside the solenoid it is constant at all points. Okay. Now you can see here I have shown that the left end is acting as a south pole and the right end is acting as the north pole. Suppose if I will change the direction of current, means then the left side will become the north pole and the right side will become the south pole. There is one rule which is called as end rule. Okay, there is a rule called end rule, and using this end rule you can find which end will be north pole and which end will be the south pole. Suppose you take, this is a solenoid, this is a solenoid. So how many end faces a solenoid has is 2. Okay, I am going to keep the solenoid close to me like this. So this end is called the nearer end and the other end is called the far end or the farther end. This is the nearer end, this is the farther end. Okay, so when you view a solenoid such that in the nearer end, if the current is flowing in the clockwise direction, when the current is entering the loop in the clockwise direction means then this end will act as a south pole. So for clockwise, okay, clockwise current in the nearer end, okay, when the current enters in the clockwise direction means that acts as the south pole. Okay, and in the farther end, okay, farther, if the nearer end the current enters in the clockwise direction means then it acts as a south pole. I told you, isn't that? How to remember this? You see here, you make this as a shape S, okay, like the alphabet S, and these two end points will indicate by arrow. End points indicate by arrow. Can you see that this arrow is in the clockwise direction? These two arrows both are in the clockwise direction, and this alphabet shape looks like with what? S. So that is why it is the south pole. Suppose if the current in the nearer end is in the anti-clockwise direction, nearer end the current is entering the first loop in the anti-clockwise direction, then the nearest pole will be north pole. Okay, then the nearer pole will be north pole. So you can remember like this. So once again I will repeat, my dear students, you take the solenoid and keep by your front side. Look at the solenoid. When the nearer end, in the nearer end, if the current is flowing in the clockwise direction means the nearer end will be a south pole and the other end, farther end will be a north pole. Suppose in the nearer end the current is entering in the anti-clockwise direction means the nearer pole will be the north pole and the farther pole will be the south pole. So this is to find the polarity of the two ends. That is why this rule itself is called as what? A end rule. So did you all understand? In the end rule you see that when the current is clockwise means it appears like a shape S. So the nearer end will be the south pole. And here the current is in the anti-clockwise direction. So the nearer pole, the current is in the anti-clockwise direction. So the current is in the anti-clockwise direction means the nearer pole will be what pole? I said it is the north pole. Okay. So for the solenoid, once again I am repeating, my dear students, there will be magnetic field only along the axis of the solenoid, that is inside the solenoid, and outside the solenoid there can be no magnetic field. Understand? What type of magnetic field this solenoid will produce is a uniform magnetic field. Uniform magnetic field means what do you understand? The strength of the magnetic field will be the same at all points. See, in the competitive exams they will ask such questions. If the strength of the magnetic field at one end will be given, what is the strength of the magnetic field at the other end they will ask, or at the midpoint they will ask. It will be the same you have to write, because everywhere the magnetic field will be uniform inside the solenoid, and such a uniform magnetic field is represented by horizontal and parallel lines. Understand? Okay. Now, what are all the factors? What are all the factors on which the magnetic field due to the solenoid depends? See, B is the magnetic field, and this B due to the current carrying solenoid is equal to mu naught into N into I This is the strength of the magnetic field inside the solenoid. And what is it equal to? Mu naught times N times I, where N is the number of turns, 1, 2, 3, 4, 5, 6, 7, 8 number of turns, like that, N number of turns. I is the current, okay, the conventional current supplied to the solenoid. And mu naught, I told you, it's a magnetic constant which is called as what? Permeability, magnetic permeability of free space. So these are the factors, 1, 2, 3 factors on which the magnetic field due to the solenoid depends. And which rule is used to detect the polarities of the two end pieces of the magnet? That rule is called as end rule. So according to the end rule, if you keep a solenoid in front of you and view the nearer end, in the nearer end, if the current is entering in the clockwise direction, means it is a south pole. So the other pole is the north pole. In the nearer end, when the current is entering in the anti-clockwise direction, means that is a north pole. Okay. The next topic is electromagnet. You can see here electromagnet. This is one type of magnet which is also called as a temporary magnet. Okay, electromagnet. So what is an electromagnet? It is an extension of the solenoid only. You see here there is a solenoidal coil which is connected to a battery, and I am going to connect this in series with a plug key. What will happen when the plug key is closed? A current will flow. Okay, a current will flow through the solenoid and a magnetic field will be produced. So this time I have taken a hollow cylinder first. Inside the hollow cylinder, air will be present. So I will measure the strength of the magnetic field. Okay, using this formula. Next time I will place a thick rod of steel or soft iron inside the core or center of the solenoid. And then for the same current and for the same number of turns, I find that the strength of the magnetic field has increased. So in the absence of soft iron or steel inside the hollow cylinder of the solenoid, the magnetic field strength I measured. And in the presence of this steel or soft iron inside the core of the solenoid, when I pass the same current, I find that the strength has increased several times. So this is the idea of making electromagnet. When I switch off the current, what will happen to the magnetism retained by this soft iron? It will become zero once again. When there is no current, means this magnetic field inside this iron also will become zero. So long as there is a current flowing through the solenoid, there will be magnetism retained inside the soft iron piece. So it is a temporary magnetism. This temporary magnet only is called as electromagnet. Okay. So these electromagnets are mainly used in electromagnetic cranes during the derailment of railway coaches, okay, and in the construction sites and all to lift the steel angles and all, such electromagnets only will be used. In other applications also, electromagnets are used in the telephone receiver, old landline telephone receivers. Then in some loudspeakers, okay, loudspeakers, even in power generating stations, now the turbine coil which is used to rotate and generate electricity also, electromagnets only are being used. So you will be studying again about the electromagnets in the other chapters also. Okay students, now finally I want to conclude with 1 or 2 points. What are the differences between permanent magnets and artificial magnets? Okay, permanent magnet and artificial magnet. Okay, permanent magnet and artificial magnet. There are some differences. See, questions may come from any angle. Okay, so list some differences between the permanent magnet and artificial magnet. First of all, permanent magnet, for example, let us take the bar magnet and the horseshoe magnet and all. Understand? This permanent magnet have fixed strength. Okay, have a fixed strength. And for the artificial magnet, when you take this case, when you increase the current, means the magnetic strength can be increased. When you increase the number of turns, okay. So by placing any other strong magnetic substance also, here the strength can increase. Okay, strength can be varied. Strength can be varied. It can be increased or decreased also. Okay, and here you see that the north pole and the south pole of a bar magnet you take for example. Suppose if a bar magnet is having a north pole and a south pole, when you reverse the magnet, north will be north and south will be south only. They cannot interchange the polarities. Okay, so polarities cannot be changed. So north and south poles. Okay, north and south poles are fixed, whereas here poles, okay, poles can be exchanged. Poles can be changed or they can be interchanged. So these are the two major differences. And also comparing to the permanently, that is a bar magnet and horseshoe magnet, the artificial magnets have greater strength. So comparatively you can write this is a comparatively less strength. Okay, so comparatively less strength only. Okay, but the electromagnets are very powerful. So this is a very high strength or very great strength. Okay, very great strength we can write. Comparing to the bar magnet and horseshoe magnet, they have a very great strength. So, okay, my dear students, we have studied about the magnetic field produced due to a straight conductor, circular conductor, a solenoid, and also an electromagnet. And what are the two rules we have studied in this is the right hand thumb rule. This rule relates the direction of the current and the direction of the magnetic field around the current carrying conductor. And the end rule is used for what? To detect the polarities of a solenoid carrying a current. Okay students, fine. Let us meet in the next new topic. Bye.